We build microchips to solve specific mathematical problems. The physical layout of a silicon die dictates exactly what kind of computation it can perform efficiently. For decades, the Central Processing Unit, or CPU, has served as the general-purpose brain of our computers, designed specifically to execute sequential instructions one after another. To execute sequences effectively, the CPU is built with a singular architectural philosophy, latency orientation. Its goal is to finish a single complex task as fast as physically possible. Looking at a modern CPU package, latency dictates the hardware. Notice the massive L2 and L3 cache blocks. These layers take up a huge percentage of the die to keep data physically close. With so much real estate dedicated to cache, few processing cores remain. Beyond the cache, CPUs dedicate limited silicon to complex control logic. They use mechanisms like branch prediction to guess which sequential steps will happen next, preparing the data in advance to shave off fractions of a millisecond. This design is perfectly suited for unpredictable sequential tasks, like running an operating system or executing a complex database query. The CPU is a machine built to minimize delay. It deliberately trades away the ability to do thousands of things at once in exchange for blinding speed on a single, highly complex thread. But modern high-performance computing and deep learning artificial intelligence place an entirely different demand on our hardware. Training a neural network relies on massive matrix multiplications. These workloads don't require complex sequential logic or branch prediction. They require millions of independent calculations to be solved simultaneously. When these workloads hit the hardware, physical constraints become obvious. In Pipeline A, a sequential task moves quickly through the CPU's large gate. But in Pipeline B, a parallel AI workload involves thousands of tiny operations that instantly jam. The CPU immediately bottlenecks. The obvious workaround is to simply pack more processing cores onto a single CPU die. However, dictated by Amdahl's law, the sequential parts of a program limit the overall speedup. Jamming extremely high core counts onto a standard CPU die forces manufacturers to lower the clock speed of each individual core to manage power and heat. More importantly, scaling CPUs for AI fails on basic silicon economics. Deep learning's matrix math doesn't need massive L3 caches or sophisticated branch prediction. If you use a CPU for AI, you waste precious physical die space on hardware features the workload completely ignores. To process artificial intelligence efficiently, we cannot incrementally scale up CPU architecture. We have to redesign the silicon economics entirely, prioritizing extreme throughput over latency. Let's look at what happens if we take a standard CPU die and ruthlessly optimize it for massive parallelism. We start with the standard, latency-oriented CPU layout. First, we delete the massive shared L3 cache layer entirely, freeing up a large portion of the silicon. Next, we strip out the complex control logic, data forwarding, and branch prediction units from the individual processing cores. We take all of that newly liberated die space and fill it with thousands of tiny, simple arithmetic logic units, or ALUs. This is the high-level architecture of a modern graphics processing unit. Looking at this diagram, you can see the layout has shifted entirely away from large cache memory layers directly into raw computation. If we isolate a single processor cluster, we can look closely at the GPU's foundational unit, the streaming multiprocessor, or SM. The SM is our new basic building block. It pairs a small, dedicated instruction cache with a highly dense grid of ALUs. By abandoning the latency optimizations of a CPU, we engineered a throughput-oriented architecture capable of taking on thousands of calculations at the exact same time. Having thousands of cores on a chip is useless if the system cannot schedule tasks for them to perform without creating a bottleneck. A traditional CPU schedules tasks to independent cores one at a time. Trying to manage thousands of ALUs this way would be chaotic and entirely too slow. To solve this, the GPU relies on a specific unit of execution known as a warp. A warp is a strictly defined group of 32 threads. Instead of moving individually, these 32 threads are grouped together and scheduled as a single block onto one streaming multiprocessor. This grouping allows the GPU to use an execution model called SIMT, single instruction, multiple thread. Under the SIMT model, all 32 threads within the warp execute the exact same instruction at the exact same time, but each thread applies that instruction to its own distinct piece of data. Fetching instructions takes time. By fetching one instruction and applying it across 32 threads simultaneously, SIMT drastically reduces execution overhead, making the ALUs hyper-efficient. A GPU achieves massive scale because it doesn't manage individual cores independently. It commands platoons of cores to march in strict mathematical lockstep. There is a critical vulnerability in our new architecture. Because we stripped away those massive L3 caches to make room for more cores, retrieving data from global memory takes a very long time. When a processor has to wait for memory to arrive, it enters a stall. During a stall, the ALUs sit idle, doing no math. Here is how a CPU and a GPU handle that exact problem. On the top timeline, a CPU is crippled by this idle time. When it hits a memory request, the core stops entirely. This is why a CPU requires massive caches to prevent these stalls from ever happening. On the bottom timeline, a GPU warp hits a memory request, but instead of sitting idle, the hardware instantly slides a second warp into place to use the ALUs. When warp 2 stalls, warp 3 tags in seamlessly. This mechanism is called zero overhead warp scheduling. Using a prioritized scheduling policy, the streaming multiprocessor instantly selects warps that already have their operands ready. This keeps the physical execution pipeline moving, preventing the stall from stopping the math. The design philosophies are completely opposed. CPUs use large caches to reduce latency. GPUs use massive thread counts and zero overhead scheduling to hide latency. As long as the GPU has enough parallel tasks to juggle, its individual ALUs will remain perfectly saturated. The memory takes a long time to arrive, but the chip is always busy, achieving a level of raw throughput that is impossible on a CPU. We see these concepts in the physical layout of real-world data center hardware. This is the die architecture of an NVIDIA Pascal GP100 GPU. Notice the immense scale. This single chip packs 60 streaming multiprocessors, representing thousands of individual cores, onto one piece of silicon. Modern systems operate on a model called heterogeneous computing. They don't force you to choose between the speed of a CPU and the scale of a GPU. They use both. The CPU acts as the host. It manages the operating system, databases, and necessary sequential logic. The GPU acts as the device, receiving the massive, highly parallel workloads assigned by the host. When mapping an AI workload onto this hardware, the synergy is perfect. In a neural network, every weight update is an independent calculation assigned to its own thread. These threads group neatly into warps, executing simultaneously across the entire array of streaming multiprocessors. Massive matrix multiplications are the lifeblood of large language models. They are the exact mathematical problem this throughput-oriented architecture was designed to solve. We reached sequential processing limits, stripped away the massive caches, packed the die with simple ALUs, executing in strict lockstep to hide the latency. The modern artificial intelligence revolution was driven by breakthroughs in algorithmic design. But those algorithms only run at scale because they finally met a hardware architecture perfectly aligned with massively parallel math.